students. The flow of today's talk is as follows. First of all, we will study the optimality criteria theorem. Then we will take an example, and thirdly we will look at the main duality theorem. Then we will talk about the complementary slackness theorem, and from them we will derive the complementary slackness conditions, and finally an exercise for you to do as a homework. So, first of all, let us look at the statement of the optimality criteria theorem. The theorem says the following: if there exists feasible solutions x and y for the symmetric primal dual LP such that the corresponding values of their objective functions are equal, then these feasible solutions are in fact the optimal solutions of their respective problems. So, what does this theorem say? It says that we have a symmetric primal dual, that is, we have all the inequalities in the constraints and all the decision variables should be of the greater than equal to type. That is the way we had defined the symmetric primal dual problem. So, in both the primal as well as in the dual, we should not have any equality constraint and we should not have any unrestricted variables. Given this primal dual which is symmetric, let us suppose that we have x and y as two solutions, that is, x is a solution of the primal and y is a solution of the dual. I mean, it is a feasible solution, not necessarily optimum. If x is a feasible solution of the primal and y is a feasible solution of the dual, such that their objective function value is same. Remember, we had defined the objective function of the primal as f. So, that means f of x, if its value f of x is equal to phi of w, that is, phi is the objective function of the dual. So, if f of x is equal to phi of w, if f of x is equal to phi of y, then these x and y are actually nothing but the optimum solutions of the respective problem. So, let us try to verify this with the help of an example. Let us suppose we have a primal problem as follows: maximization of f is equal to x1 plus 2x2 plus 3x3 plus 4x4 subject to x1 plus 2x2 plus 2x3 plus 3x4 is less than or equal to 20. Second constraint is twice x1 plus x2 plus 3x3 plus 2x4 which is less than or equal to 20, and all the variables, that is x1, x2, x3, x4 should be greater than or equal to 0. On the other hand, the dual of this primal can be written as minimization of phi is equal to 20 y1 plus 20 y2, and this is subject to the following four constraints: x1 plus twice x2 greater than or equal to 1, twice y1 plus y2 greater than or equal to 2, twice y1 plus 3 y2 greater than or equal to 3, 3 y1 plus 2 y2 greater than or equal to 4, and y1 and y2 are greater than or equal to 0. Now, you will observe that this is a symmetric form of the primal and the dual, because there are no equality constraints in either the primal or the dual, and also there are no unrestricted variables either in the primal or in the dual. Now, if we solve the primal and the dual, we get the following feasible solutions. If you look at this point 0, 0, 4, 4, this is a feasible solution of the primal, and similarly 1.2, 0.2, this is a feasible solution of the dual. You can check that both these points satisfy their primal and their dual respectively. You can check this by substituting them in the constraints and make sure that they satisfy all the constraints. So, that is the definition of feasibility. Next, let us look at the objective function value of these two feasible solutions in their respective primal and the dual. So, for 0, 0, 4, 4, we will substitute this in the objective function value of the primal, that is f, and similarly we will substitute 1.2, 0.2 into the objective function of the dual, that is phi, and we find that both these values come out to be 28. Now, this is not a chance. In fact, we have got these two feasible solutions of the primal and the dual such that their objective function values of their primal and the dual is same. Therefore, by the theorem that we have, these are actually nothing but their optimal solutions, because their objective function values is same. Next comes the main duality theorem. It says that if both the primal and the dual problems are feasible, then they both have optimum solutions such that their optimal values of their objective functions are equal. Now, this is an interesting result. It tells us that we can get optimum solutions of the primal and the dual provided we have feasible solutions of the primal and the dual. Next comes the complementary slackness theorem. Now, according to this theorem, if the primal is of the type maximization of f x, which is equal to C transpose x, subject to a x less than or equal to b, x greater than or equal to 0, and similarly the dual is minimization of phi of y is equal to b y, subject to y a is greater than or equal to c, y is greater than or equal to 0. So, this is nothing but the symmetric form of the primal and the dual. Now, let x naught and y naught be the optimal solution of the primal and the dual respectively. That is, x naught is the optimum solution of the primal. Similarly, y naught is the optimum solution of the dual. Then the optimality conditions are satisfied if and only if. If and only if means if this condition is satisfied, then it is both ways basically. So, what are these conditions? These conditions are y naught a minus c multiplied by x naught plus y naught multiplied by b minus a x naught. This should be equal to 0. So, these are called the complementary slackness theorem. That is, at the point of optimality, that is x naught and y naught, we have this condition should be satisfied, and similarly if there are two points x naught and y naught which satisfy this condition, then they are nothing but their optimum solutions. So, that is the meaning of if and only if. Now, let us verify this optimality conditions. In the previous example that we took, the point 0, 0, 4, 4, this is primal feasible, and similarly 1.2, 0.2, this is dual feasible, and their value of their objective functions is 28. So, therefore, we want to make sure whether this condition holds or not. So, y 0 a minus c multiplied by x naught plus y naught multiplied by b minus a x naught, this should be equal to 0. Let us see what happens if we put the values of all these variables in the left hand side of the equation. So, I will break it into two parts, the first part and the second part. The first part is as follows, that is y 0 a minus c x naught. Now, what is y 0? Y 0 is the point of the dual, and that is nothing but 1.2, 0.2. Similarly, what is A? A is the coefficient matrix of the constraints, that is 1, 2, 2, 1, 2, 3, 3, 2, right, minus C. What is C? C is nothing but the coefficients of the objective function of the primal, that is 1, 2, 3 and 4. Then we have x naught. Now, what is x naught? X naught is the feasible solution of the primal. It is nothing but 0, 0, 4, 4. Now, when you substitute these values into the equation, you have to make sure that the matrix multiplication is defined, and that is the reason why you have to be very careful with writing the matrix in the row form or in the column form. Now, when you multiply this and you solve it, simplify it, you get the answer as 0. I would like you to verify for yourself whether these calculations are okay or not. So, you can check that finally, the first part of this conditions, complementary slackness conditions, the first part is 0. Similarly, the second part. Now, the second part says y naught multiplied by b minus a x naught, and we will substitute the values of y naught. What is y naught? It is the optimum solution of the feasible it is a feasible solution of the dual. It is 1.2, 0.2. Similarly, b, what is b? B is the right hand side of the dual, that is 20, 20, and then the A matrix is 1, 2, 2, 1, 2, 3, 3, 2 multiplied by x naught, that is 0, 0, 4, 4. So, that is what you get equal to 0. So, we have shown that the optimality theorem conditions hold. Next comes some complementary slackness conditions. So, we will study some of the complementary slackness conditions. They are as follows. Number 1, if a primal variable is positive, positive means strictly positive, it is not equal to 0. If a primal variable is positive, then the corresponding dual constraint will be satisfied at the optimum as an equation. It will be an equality at the optimum. Let us verify this condition. Look at the third variable of the primal solution. It is 4. The third variable of the primal solution is 4, that is, it is strictly greater than 0, and correspondingly the third constraint of the dual is twice y1 plus 3 y2 greater than or equal to 3. Now, according to this condition, this should be satisfied as an equality. So, let us verify it. This is satisfied as an equality of the dual optimum. Now, the dual optimum, we will substitute 1.2 comma 0.2 into this inequality. So, what you get? 2 multiplied by 1.2 plus 3 multiplied by 0.2, which comes out to be 3, and that is what is the right hand side. So, according to this condition, if there is a variable which is primal, which is greater than 0 at the point of optimality, then the corresponding dual constraint is satisfied as a equality at the optimum. Second condition, if a primal constraint is a strict inequality at the optimum, then the corresponding dual variable must be 0 at the optimum. Again, very interesting to note, that is, if there is a primal constraint which is a strict inequality, means it is not less than equal to, it is only less than, and similarly it is not greater than equal to, it is only greater than. So, it says that if the primal constraint is a strict inequality at the optimum, then the corresponding dual variable should be 0 at the optimum. Let us verify this. Let us say if we have a dual variable which is positive, then the primal constraint will be satisfied as an equation at the optimum. Look at the first dual variable. What is the first dual variable at the optimum? It is 1.2, and if you look at the first primal constraint, what is the primal constraint? It is 2x1 plus 3x2 less than or equal to 20. Now, this is satisfied as a equality at 0.0044. So, hence this is verified. Next, the fourth condition. If a dual constraint is a strict inequality, then the corresponding primal variable must be 0 at the optimum. Now, the third dual constraint is y1 plus 2y2 greater than or equal to 1. This is a strict inequality at the point 1.2 comma 0.2. Now, corresponding to this first primal variable, this is 0 at the optimum. So, what do we conclude? We conclude that there is a relationship between the positiveness of the primal variable and the less than equal to or equality of the constraint of the dual at the point of optimality. Please note, these conditions are valid only at the point of optimality, not necessarily for the feasible points. In conclusion, we can summarize the primal and the dual relationship like this, assuming that the primal is the maximum and the dual is of the minimization type. Remember, if the primal is of maximization type, then the constraints should be less than equal to type. Similarly, if the dual is of the minimization type, then the constraints should be greater than equal to type. So, therefore, what is the relationship? If the primal has a coefficient A, that is the Aij of the constraints, the coefficients, then the transpose of the coefficient matrix has to be taken for the dual. Similarly, B is the right hand side of the primal, then that becomes the cost vector of the dual, that is it becomes the coefficients of the objective function. Similarly, if C is the price vector or the cost vector, that is it is the coefficients of the objective function of the primal, then that becomes the right hand side vector of the dual, as we have seen. Next comes the constraints. At the point of optimality, if the ith constraint is an equation at the point of optimality, then the dual variable is unrestricted in sign. Sorry, if ith constraint is an equation, this is regarding the asymmetric nature of the primal and the dual. That is, if the ith constraint is an equation, then the corresponding dual variable is unrestricted in sign, as we have seen in the previous lecture. If a variable xi is unrestricted in the primal, then the dual constraint is an equation. So, that also we had seen as the asymmetric primal dual. If ith constraint is of the less than equal to type, then the dual variable, corresponding dual variable yi will be greater than or equal to 0. Similarly, if the ith constraint is greater than equal to type of the primal, then the corresponding dual variable yi will become less than equal to 0. And of course, we have to look at xi's are greater than or equal to 0, then the jth dual constraint is greater than equal to type, and similarly if xi is less than or equal to 0, then the jth dual constraint is less than equal to type. So, in this table what we find is, we conclude that there is a beautiful relationship between the primal and the dual, and similarly the decision variables of the primal are related to the constraints of the dual. So, we come to this end of this lecture, and before we depart, we would like you to do this exercise. Write the dual of the following LPP and what can you say about the solutions of the primal and the dual. So, you need to use the theorems that we have learned and find out a relationship between the primal, the solutions of the primal and the dual. So, the objective function is to be maximized. Z is equal to 3x1 plus 4x2 subject to 7x1 minus 2x2 greater than or equal to 4, and similarly minus 3x1 plus x2 less than or equal to 3, x1 is greater than or equal to 0 and x2 is unrestricted in sign. So, I hope you have noted down this question and you will be able to find out the solution to the problem. Thank you.